Hello, everybody. Let's see you again. And let's start our lecture. Okay. Today, we will be continuing study acoustic sensor and electrostatic or capacitive ultrasonic transducer consists of two flat conductive plates, one fixed to the housing and other movable relative to the fixed plate, and together constituting a flat capacity, as you can see on figure A here on the slide. For this construction, the equation V proportionals Q over C, and C equals epsilon naught times epsilon R times A over D small. And in the receiver mode, the moving plate is charged with a more or less constant charge, which is realized by the connecting the plate via a resistor to a rather big DC voltage of some 100 volts. Sound waves, moving air particles, bring the plate into the motion, and due to the constant charge and the charging plate distance, the voltage across the plates varies in accordance with the sound wave. To obtain a high sensitivity, the plate is made very thin and flexible, resulting in an enhanced acoustic coupling to the air. We will be seeing these on sections during studying lecture or lecture on acoustic impedance. But obviously, the sensitivity is also proportional to the DC voltage on the movable plate. The necessity of an external high voltage is a major drawback of the electrostatic transducer. An alternative to such an external voltage is the electret version, in which a charge is permanently stored in a sheet of a suitable piezoelectric material, making up the fixed plate of the capacitor. Such electret or electret condenser microphones for air-coupled application operate mainly in the audible range. It means from 20 Hz to 20 kHz. In the transmitter mode, an AC voltage is put on the movable plate of the capacitor. A voltage difference V between the plates results in a force equal to, as you can see on this first equation here. And with S here, the surface area of the plates, and D small in this slide is the gap distance. Since this electrostatic force, explaining the name of this type of transducer, is proportional to the square of the voltage, as you can see on this part of this equation, it is always constructive, driving the movable plate toward the fixed plate until it is in equilibrium with the counter force of the elastic bond. Should the plate move linearly proportional to an applied AC voltage to generate the proper sound waves, the capacitor should be biased with a DC voltage higher than the amplitude of the AC voltage. And this equation also shows that the sensitivity of the emitter increases with decreasing initial plate distance. To make a robust transducer with small initial curve and a thin movable plate, as sometimes you might call them membrane, the latter is sustained not only at its edges, but over a large part of the surface, as you can see on a figure B, accomplished by a groove plate or other isolating structures like a grid or net. But obviously, the membrane only vibrates at place where it is free to move. This multimode vibration explains the large deviations in the directivity diagram of real electrostatic transducers as compared to those given in this slide. Moreover, the layout of the structure strongly determines the frequency characteristics of the transducer. On the other hand, it allows designers of electrostatic transducers to optimize transducer characteristics for particular applications. Like many other sensors, ultrasound transducers can also be manufactured using silicon technology. The membrane in such devices is made from silicon by anisotropic etching, similar to the piezoresistive pressure sensor discussed in lecture of resistive sensors earlier. I hope you remember this. Okay. It acts as a movable or vibrating electrode of a capacitor-like structure. An important advantage of this technology is the ability to make large numbers of membranes on a single chip. Silicon membrane sensors have a smaller bandwidth due to the multimode resonance frequencies of the mechanical structure. The output power and sensitivity are substantially less than the micro devices because of the much smaller dimensions and deflections of the micro. A piezoelectric acoustic transducer consists of a piece of piezoelectric material configured as a flat plate capacitor. Let's look at this slide. An AC voltage applied to the crystal causes the material to vibrate, resulting in the generation of acoustic energy. Conversely, when the crystal is deformed by incident sound waves, a piezoelectric voltage is induced. Hence, the transducer must be used in transmitter mode and in receiver mode, similar to the electrostatic transducers, but without the need of a biasing DC voltage. Do you agree? Irrespective of the application, the transfer of sound energy from transducer to medium or vice versa is crucial for the S-N ratio of the measurement signal. As explained today, the transfer is governed by the acoustic impedance of the material involved. Obviously, since a piezoelectric ceramic material has a high acoustic impedance compared to air, the efficiency of power transfer to air is extremely poor. Also, for every liquid or solid medium, power loss can be considerable too. In case of a solid, air voids between the transducer and the solid significantly lowers the transmission efficiency, a problem often encountered in acoustic non-destructive density of objects. In such applications, a coupling gap between the transducer and the solid objects under test is essential. There are many ways to improve the transmission of sound from the transducer to its acoustic environment. However, efficiency is not the only characteristic of the interest. Bandwidth and beam shape are equally important parameters. optimization is often a compromise between these parameters. The advanced models of the acoustic arrangement based on transmission line are required to find an optimal solution for a particular application. Basically, there are two major approaches: matching layers and shaping. The first is usually applied for liquid and solid contact, as you can see on a figure A. Two essential parameters of such layers are the acoustic impedance and the thickness. The acoustic impedance of the matching layer should have a value between that of both materials at the either side of this layer. According to very simple model, the optimal value is the harmonic mean of these two values. But in practice, other values appear to be more effective. The thickness of the plate should be equal to a quarter of the sound wavelength to minimize the reflection of the front side of the matching layer in favor of the transmitted waves. Having found the optimum impedance value, the next problem is finding a material having that particular impedance. Matching layer design is still the subject of continuous research, including the search for suitable materials, the use of multiple matching layers and backing layers, extension to the frequency range, and manufacturing issues, like the influence of the glue between the layers and the use of silicon-compatible technology. To overcome the enormous mismatch in airborne applications, the transmission efficiency is improved by placing a precisely shaped piece of an acoustically soft material on the front side of the ceramic element, like a tiny horn as shown in figure D. A horn or cone also affects the frequency range as well as the radiation field of the transducer. Most commercial low-cost piezoelectric transducers are provided with such a horn. Cold PVDF has a relatively low acoustic impedance, as you can see in this table, making it an attractive material for ultrasound applications. The flexibility of the material allows operating in bandwidth mode, whereas the ceramic sensors usually operate in thickness mode. Other piezoelectric materials have been studied for their suitability as acoustic transducer, or another saying, porous field with artificially electric dipole. Piezoelectric transducers operate best at resonance. The high stiffness of ceramic material results in a narrow bandwidth. In other words, a high mechanical Q factor. The resonance frequency is determined by the dimensions of the crystal, and to lesser extent by the matching element. Popular frequencies are 40 and 200 kHz. Many acoustic detection systems use tone bar signals. A typical response of a piezoelectric transducer to a bar signal at the resonance frequency is shown in this figure. Apparently, the output part shows strong distortion of the edges due to the narrow bandwidth of the device. This has important consequence for the determination to the TOO measurement, as will be explained a bit later during today's lecture. As shown in the beginning, the beam width of a sound emitter is determined by its lateral dimension and the frequency of the emitted sound signal. With a properly designed array of transducers, a much narrower beam can be obtained using spatial interference of the individual acoustic signal. For points in the hemisphere where the travel distance differ a multiple of the wavelength, the waves add up in P, in point P, as you see, or in other points, as in Q, the waves partially cancel. Moreover, the direction of this beam can be controlled over a limited range, plus minus 30 degrees, with the phase difference of the applied electrical signal. Similarly, the sensitivity angle of an acoustic transducer operating in receiver mode can be narrowed using an array of such receivers. At the receiving side, the individual outputs are added after a properly chosen time delay. By controlling the delay time, the main sensitivity axis can be varied over a limited angle. The application of this general principle to acoustic transducers has already been described in earlier literature. Due to improved technology phase array, the gaining interest for acoustic ranging and imaging. They eliminate the need for the mechanical and slow scanning mechanism, but have a limited angular scanning range. In general, at an increasing deflection angle, the amplitude of the side lobe, let's look at this figure, please, increases as well, deteriorating the beam quality. The majority of acoustic distance measurement systems are based on the TOF method, a measurement based on distance-dependent attenuation, as we slide, is rather susceptible to environmental influences and the absorption properties of the object involved. In most acoustic TOF systems, the elapsed time between the excitation of a sound pulse and the arrival of its echo is measured. Since the transduction effects are reversible, the transducer can be switched from transmitter to receiver mode. We see only one measurement. The travel distance x follows directly from the TOF T and from left to right side, and using the relevation V sub A. So this value is proportional x over t for direct travel, right? Or VA proportional to x over t for the echo system, where the sound waves travel twice the distance. Are you agree? Okay. The sound signal can be of any shape. Most popular are the bars, a number of periods of a sine wave, a continuous wave with constant frequency, and the FM modulated sine waves, or chip. We discussed the major characteristic of these three types. Pulses and bandwidth limited Gaussian noise are the other possibility. The tone part is the most common signal type used for acoustic distance measurements, in air especially, in particular for applications where high accuracy is not required, like ranging, navigation, obstacle avoidance. A transmitter emits a short pulse, a few up to about 10 periods of a sine wave, in the direction of an object. The sound reflects in accordance with the reflection properties of the object surface and its orientation. As discussed earlier, travels back and received by the same or a second transducer, which detects the moment of arrival. Due to the various causes, the accuracy of TOF measurement, and so the distance measurement is limited. First, there is noise of electrical and acoustical origin. which becomes important and larger distance. When the echo signal is low due to the divergence of the sound waves. And next, spurious reflections can also mark the arrival time of the main echo. A further cause of inaccuracy is the unknown orientation of the reflecting surface relative to the main axis of the transistor. And finally, the narrow bandwidth of a piezoelectric transducer makes the edges of the path less pronounced, obstructing an accurate detection of the starting point of the path. Some, but not all of these causes are typical for the path missing. In case of an individual transmitter and receiver with spacing, as you can see on a figure A, the measurement distance x stretch, you can see in this formula, expressed square root from a squared over 4 plus x squared. As you may see, from which is followed the relative error of the delta. So, for a distance x equals 3.5 times the space between t and r, the relative error is only 1%, which is acceptable in most practical situations. A tilted reflection, as you can see, reflecting surface, as you can see on figure B, introduces a typical cosine error. Look in this angle, or this angle, it's identical. Of minus cosine angle proportional minus half alpha. Alpha measured in radian, right? Only waves normal to the surface will return to the receiver. As an example, as we see, a 1% error occurs when the tilt angle is about 8 degrees. But we should note, however, that the sound intensity is reduced according to the directivity. When in this numerical example, the half angles of the balls R and T are also 8 degrees, the intensity of the echo has dropped by a factor of half. It means 4. When a signal transducer is used, switching from transmitter to receiver mode is only possible after the complete path has been transmitted. This limits the minimum detectable distance. There is a dead band or dead zone, equal to half of the number of wavelengths, because sound is traveling twice in the distance, right? Shortly, the pulse duration reduces this dead band, but also the sound energy, and hence the SN ratio is reduced. The response of a piezoelectric transducer on a bus shows a rather large rise time due to the high quality factor of this transducer type. Actually, this effect occurs twice, first at the transmitter and the second time at the receiver. The starting point of the echo is easily obscured by noise. The most common detection method for the echo burst is a threshold applied to the receiver signal. The TOF is set by the first time to the echo exceeds the threshold. The threshold must be well above the noise level to prevent noise being interrupted at the incoming echo. On the other hand, when the threshold is too high, one or more periods of the received signal can be missed, as shown namely in this video. At nearly 40 kilohertz, this results as an error of a multiple of about 8 millimeters, which is the penalty for this simple signal processing scheme. Many methods have been published over the past year, all aiming at a higher accuracy of the bar's TOF measurement, despite noise and other interfering effects, such as temperature changes and air turbulence. One such approach is to use the complete echo signal and not just the starting point to determine the TOF, like by autocorrelation or cross-correlation. These techniques yield typical error below 1 millimeter, depending on the SN ratio and the travel distance, but need longer processing time. Another approach is based on knowledge about the shape of the equals envelope, which is determined by the transducer's transfer function. Alternatively, instead of the starting point of the equal signal, where the SN ratio is low, the arrival time of a point around the maximum amplitude could be chosen as a measure for the TOF. With this method, the typical distance error can be less than even 0.1 millimeter. Other researchers use the phase information comprised in the echo signal, the typical shape of the envelope, or just more advanced signal processing techniques. Noise as the input signal is studied too. The average output power of a path is relatively small and may result in a poor SN ratio, in particular at increased distance. In this respect, the emission of a continuous acoustic signal is better. Distance information is obtained from the phase difference between the transmitting and receiving waves. This method has two main drawbacks. First, emission and detection cannot share the same transducer. Hence, two transducers are required, making the system larger and more expensive. It also introduces crosstalk because sound waves propagate through the construction directly from the transmitter to the receiver giving signals, and that may be larger than the echo itself. And second, the unambiguous measurement range is only one period of the sound wave. The resolution, however, can be very high. For instance, 1 degree phase resolution and 7 millimeter wavelength correspond with a distance resolution of 19.4 micrometers. Further, there is continuous information about the measured distance. So, for distance control of a short range, the CV method is preferred over the fastness. CV, I say it means CW as a sine wave. Sorry, okay? The unambiguous range can easily be enlarged by amplitude modulation, as you can see on a figure 8. Suppose the transmitted signal is an AM signal, amplitude modulated signal, described by the general expression as you can see at this figure, at this equation on the top, please. For V sub t, its proportional amplitude in brackets 1 plus m cosine omega st out of the brackets times the cosine omega ct. Omega c here is the carrier frequency. In case as a omega s is the modulating frequency. And usually omega s many times less than omega c. When using piezoelectric transducers, the carrier frequency should equal the resonance frequency. The spectrum of this modulated signal contains the components omega c plus omega s, and omega c minus omega s, as you can see on figure E on the top. All components should fall within the bandwidth of the transducer, even when using a piezoelectric type. It means that the period time of the envelope is much larger than the wavelength of the carrier. The received wave delayed over the TOF. We change this expression TOF as a tau, is written, as you may see, in previous equation. Just 1 second, so this expression for V sub R. So the phase difference of the carrier is Phi equal omega C times tau, or TOF. That of the envelope P equals omega tau. So for a TOF corresponding to the one period, usually equal to pi, right, of the envelope. And the carriers gets shifted over omega C over omega S as many periods. Obviously, the unambiguous range is increased by a factor of this omega C over omega S when using the phase of the envelope signal to be reconstructed by, for instance, a rectifying sequence. The method has the advantage of the continuous mode, but with enlarged range. And here, also the accuracy of the TOF measurement is limited by the resolution of the phase measurement and the uncertainty in sound velocity, according to our previous equation. And generally, the carrier and modulation frequencies are 40 kHz and 150 kHz respectively, corresponding to a low frequency period about 2 meters. Using a digital phase detection circuit, an accuracy of 2 millimeters over a 1.5 meter range was obtained. The unambiguous range of the continuous mode can be increased by frequency modulation of the sound wave. And this figure shows the transmitted in top, and we have a symbol EV, T transmitted, and frequency and received signal, V sub R, sometimes called a chirp, referring to the whistling of some bells. Assume the frequency varies linearly with the time, and starting from a lowest value, F from L, is a sub L, and increasing with the rate of K. According to this expression, F from T proportionals FL plus KT. Due to the time delay of the reflected wave, its frequency in the same time frame is proportional to the Ft equals FL plus K. In a bracket, we have T minus tau. At any moment, within the time period T sub L, where the signal occurs simultaneously, the frequency difference between the transmitted and the received waves equal. Let's look at the first expression here for expression for delta F. It's a proportional F low plus KT and minus in bracket F low plus difference K with difference type T and tau, or simply delta F proportional K tau. Apparently, this distance is directly proportional to the frequency difference and unambiguous over time T, as illustrated in this figure. This method combines the advantages of the first two methods. The transmitted signal is continuous, that is favorable for the Fn ratio, uninterrupted distance information, and the range is large determined by the frequency speed. Disadvantages over the parts method are the more complex interfacing and the fact that only wideband transducers can be applied, since the frequency varies. Further, since transmission is essentially continuous, two transducers are required for simultaneous transmitted and received. Important parameters of this system are the sweep length, the start and stop frequencies, and the sweep rate K measured in hertz per second. The sweep length should correspond to the largest distance to be measured to guarantee sufficient time overlap between the transmitted and reflected wave. The start and stop frequencies are set by characteristics of the transducer. Electrostatic transducers for low-cost applications have a rather limited frequency range, typically from 50 to 100 kHz. So just one octave, a factor of 2. And usually, the size of an electrostatic transducer in this frequency range is larger than that of a piezoelectric transducer. And this may be a disadvantage from the viewpoint of construction. However, as has been shown, the half angle is much smaller, contributing to a better FN ratio of the echo signal. According to the equation, the distance measurement requires the determination of the frequency difference between transmitted and receiving signal. Usually this is done by some correlation procedure performed in the digital signal domain. This has the advantage of a noise reduction, depending on the type of filter, but the disadvantage of the need to digitize the sample both signals. However, the procedure is essentially based on the multiplication of both signals, followed by some filtering. The basic goniometric relation of equation is used for these expressions, as we can see for alpha and cosine and beta for cosine. So, multiplying two sine waves result in a signal, as you can see here, multiplication, containing some and different frequencies. Now, let the transmitted FM signal be X sub R, sub T, and the reflected wave signal, delayed over time tau, becomes as this equation as we can see here. So this we have expression of delay of tau. The product of these two signals contains components with some and different frequencies. Since we are only interested in the frequency difference, the much higher frequencies are filtered out, and what remains is of the form, as you may see for this final equation. After transformation, we can get simply as the C times cosine 2 pi. And in a figure bracket, we get 2 delta ft plus pi from tau. And this clearly shows that multiplication procedure, a signal containing the frequency difference. Obviously, for an accurate determination of this frequency, all other components due to the multiplication procedure, as well as noise, should be sufficiently suppressed by some method of filtering. A treatment of the various signals processing algorithm goes beyond the scope of our lecture. To get an impression of a possible output, this figure presents the result of TOF measurement based on our technique with much filtering applied to the signal reflecting from the flat surface at 1 meter distance. The horizontal time scale corresponds to the delay time, or TOF, in left figure, figure A. The full scale is just the cycle period, 100 microseconds. At around 0.006 seconds, a pronounced maximum is noticeable, as you can see in the green field. In the zoomed version on a figure B, this peak appears to occur at exactly 5.95 milliseconds, corresponding with a distance of 0.1 and 0.202 meters at a measured sound frequency of 343 meters per second. And these figures also show that the resolution of the measurement is limited. Due to noise, it may happen at the adjacent peak, and that has a many larger amplitude, introducing to error to the TOF determination. Whether bar mode or continuous mode should be applied strongly, depends on the requirement and the application. In general, the Barth method is simple to realize, but is discontinuous and noise sensitive. This method is less sensitive to noise, but requires more complicated interfacing and certainly as a signal processing tool. Generally speaking, this method outperforms the Barth method in terms of range and noise immunity. Common to all methods considered thus far is the accurate determination of the time delay of an acoustic wave. Apart from the three signals discussed, many other signal types could be used to measure the TOF. Assuming the total transfer from transmitter, acoustic medium, and receiver is linear, which is the case in the majority of the applications considered here. Any signal containing some time discriminating parameter will do. A short needle-like pulse is one of these. However, the bandwidth of most transducers is too small for handling such signals, and moreover, for air applications, the energy content is too low. Gaussian noise is another one. The autocorrelation of wideband Gaussian noise is a narrow peak. When such a noise signal is applied to the transmitter, cross-correlation with the received signal results in a narrow peak in the correlogram at position equal to the TOF. The limitations of this method are mainly of a practical nature. The noise signal and the transducers are always band limited while sampling. So AD conversation and the finite measurement time further limit the resolution and accuracy of our digitally processed signal. Another approach is phase shift or frequency shift key. The signal is a sinusoidal carrier modulated in phase or frequency by a binary coded signal. Such signals are now widely used in telecommunications, but may also play a role in acoustic distance sensing. An example of an application of binary phase shift in signals for acoustic distance measurement in air. Let's start with application. The versatility of ultrasound sensing is widely recognized. Ultrasonic sensors are extensively used in the processing of industry for a variety of parameters. but they can also be found in numerous other fields, such as transportation, medical diagnostics, material research, and so on. The focus of our lecture is on the application of mechatronics for a variety of tasks with distance as the basic measurement quantity. These tasks comprise movement control in production machines, obstacle avoidance in traffic, navigation of automatic guiding, object recognition and inspection, and many, many more. Acoustic sensors are cheap, small, and easily mountable on in a mechatronic construction. When moderate distance accuracy is required, the interfacing can be kept simple. All measurements are based on the TOF principle as outlined in the previous lecture. Here is review two main tasks, navigation and inspection. Acoustic transducers are suitable for short-range navigation in structured or unstructured, or sometimes called unknown environment. Application examples are mobile robots, like pathfinder and collision avoidance. Okay? A for visually impaired people and localization of tools in a workspace. Common of these applications is the extraction of 2D or 3D information about the relative position of persons and objects in a mostly unconditioned environment. The easiest task is collision avoidance, because the demands with respect to accuracy and speed are not severe. Depending on further requirements, various options can be considered. A simple anti-collision system for robots and other vehicles like cars and wheelchairs consists of a number of fixed transducers at the front or around the circumference of the vehicle. The method works well if the reflecting obstacles have significantly large dimensions, at least a few wavelengths of sound signal, and is oriented perpendicular to the main axis of the transducer, and in the absence of multiple echoes. When the reflecting surface is not perpendicular to the main axis of the transducer, the error is introduced, as you can see on a figure B represented here. As a consequence, the range data obtained by an acoustic scanning system show the typical behavior as seen in the sonar maps in this figure. The transmitter or receiver combination rotates over an angle alpha with respect to the surface normal, and the dots represent measuring points. Range data are only available when the echo signal exceeds the detection threshold. Assume that this happens only when the reflected beam falls within the half angle of the receiver. An arbitrary choice, because the threshold level may be adjusted to any other value. In figure A, range data lie on an arc scanning with twice the half angle of the transducer. In case of a rather sharp edge, as in figure B, the acoustic wave reflects away from the receiver, so no echo is received. In practice, however, such an edge devices an echo regardless, but only over a small scanning angle. In figure C, the received echo over wave transmitted into the direction of the edge is mainly the result of a multiple reflection in that edge. As can be seen in figure B and C, even a small rotation angle results in a rather large distance error. Obviously, in these cases, the detectivity depends greatly on the angle between the two surfaces. erroneous distance data can be avoided by narrowing down the beam angle of the transmitter and receiver. But this is at the expense of the lost data points, so-called dead angles. Similar to the optical system, the ultrasonic counteract may be disturbed by spurious signals from other sources or unwanted reflections. In a natural, unconditioned environment, spurious echoes are unavoidable. When such echoes interferes with the main echo, phase information is easily corrupted, even when the amplitude of the unwanted echo is small. System uses the TOF determination by thresholding detection are rather insensitive to this phenomenon. Time windowing may suppress most of the unwanted echoes since the direct waves arrive first in time. In system based on envelope detection, such spurious echoes might introduce large TOF errors as shown in this figure. More advanced detection methods are required to overcome this problem. The performance of acoustic echolocation in air is further determined by the power and frequency of the emitted pulse. Typical working distances of low-cost anti-collision systems range from tens of centimeters, limited by dead zone, to a few meters. Ultrasonic distance sensors are also widely used in consumer products, from the sometimes inaccurately named parking radar system to distance measurement in photo cameras. Polaroid introduced the ultrasonic ranging sensor P6500 in 1981 for its autofocus camera model, shown in this picture. This particular sensor also found its use in robotics as obstacle sensor in early mobile rovers or walking machines. The system in this camera used electrostatic transducers, which were rather complicated to interface to other systems. Current designs of ultrasonic range finders have a similar range up to several meters, but use piezo transducers, which can be used at lower voltage. Integrated modules are available either with a single transducer, which needs to switch from transmission to receiving mode after transmitting a pulse of sonic pulses, or versions with two transducers, usually a matched transmitter-receiver pair. Ultrasonic range finding is an excellent technique for the exploration of an unknown environment. To find the position and orientation of a robot in a known environment and to navigate. There is an overwhelming number of papers on this topic, dealing with many kinds of system concepts and signal processing algorithms. Most of these concepts are applied for autonomous navigation without beacons. Navigation with acoustic beacons is a low-cost alternative for the optical beacon systems discussed in optical sensor lecture. Important design consideration is that the whole environment, like walls, obstacles, and persons, fall in the field of view of the sensing system. So not only in the direction of movement, but also sideways and backward. Three approaches can be followed. First, many transducers fixed all around the robot. Second, a rotatable T over R combination on top of the robot. And third, fixed transducers while using the robot itself as scaffold. An example of this first approach in which an angular accuracy of less than 1 degree using 8 transducers is reported. An obvious advantage of a mechanical scanning system is the need for just one or a very few pair of transducers. The scanning, however, is slow. A further point of consideration is the directivity of the transducer. A high lateral resolution over a wide viewing angle, possibly up to 360 degrees, requires a large number of transducers with high directionality. The same coverage can be achieved with fewer transducers but with reduced lateral resolution. Due to the relatively large wavelengths of ultrasonic sound in air, the lateral resolution is rather low. This complicates the detection of small-sized objects or to distinguish between closely spaced objects, which is important in application. Application like a floor cleaning robot or navigation system for blind persons. Enhancement of the lateral resolution without greatly increasing the number of transducers or their directivity, which is limited anyway, right, can be achieved by more advanced signal processing or potential fields applied for the wheelchair navigation and one transmitter, three receiver configuration. A well-known method is the convolution of the echo signal with the transmitted signal. This may potentially improve both the lateral and the radial resolution of an echolocation system, as is shown in this figure. This figure shows the outcome of an experiment with two coffee cups placed on a flat table. The rotating piezoelectric transducers are positioned in the origin. Due to the wide beam angle, the two cups are seen as a one object. By deconvolution, using the known pulse response of the transducers, they can be distinguished separately. Another approach to handling multiple objects, where the information from the echo amplitude is also used to construct a sonar map. Navigation of vehicles or robots can be accomplished by a totally different approach based on beacons. Such beacons can be transmitting, receiving, or passing. In case of receiving beacons, the robot generates continuous or intermittent signals all around. From the signals received by the beacons, the distance to the robot can be derived. With known beacons position, the position of the robot is easily derived, as you can see in this figure. In general, a minimum of 3 beacons is required to determine unambiguously the robot's 2D position in an open space. There is, however, also one. Transmitting beacons send out unique signals picked up by a robot equipped with an omnidirectional receiver. From these signals, an onboard robot computer determines its distance from the beacon and subsequently its 2D position. A combination of these two possibilities is applied in the accurate docking system for AGV. In a system with passive beacons, the robot transmits and receives signals reflected by the beacon. Concerning the beacons, this is by far the most simple and flexible concept. They need no power supply, and the only requirements are on accurately known position and sufficient reflectivity for the signal. A disadvantage is a high demand on environmental conditions to prevent spurious reflection. This particular application of ultrasound sensing has attracted increased interest over the last few decades. Researchers have developed various concepts based on ultrasound ranging, like electronic dogs, canes, belts, and heads, all comprising some acoustic ranging devices. Fixing the acoustic transducers Somewhere on the body leaves the hands free. Attaching the transducers on a person's head allows exploration of the environment in a more natural way. The detection area of the transducers may also be adapted to the immediate need and situation. For this application, it is important to not only avoid obstacles, but also to characterize or identify objects in the person's immediate environment. This method yields such information, but the number of classes is very limited. The technical problems to overcome are similar to those encountered in robot navigation. A particular challenge is the demand for the safe operations outdoors or in a noisy, heavy, unstructured, and unconditioned environment. A completely different approach to many of these systems is still in the experimental phase, but there is noticeable progress in performance. With the availability of cheap cameras over cars, nowadays, navigation tools are being developed based on a combination of acoustic ranging and vision. When a moving object is provided with a sound source, its position and orientation can be determined by using a set of acoustic sensors located at fixed points in the working space, similar to the beacon concept discussed a bit earlier. In this way, the 3D position of the end effector of a robot or its orientation with respect to a reference plane can be determined. A different approach combines a 2D vision system fixed above the manipulator and an acoustic distance sensor together enables 3D positioning of the robot gripper with respect to the object. Another example is the localization of surgical tools, where position accuracy of 40 micrometer is reported. In all these applications, special care should be taken to secondary echoes from floor, walls, and other objects in the surrounding field. They may cause phase error and a shift in the envelope torque of the received signal, of which the consequences have already been discussed. This figure illustrates a situation where reflection via the ground floor may cause interference error. Assume the sound frequency is 40 kHz, corresponding with a wavelength of 8 millimeters. When the path difference equals an odd number of half wavelengths, like 4 millimeters, 12 millimeters, and so on, destructive interference of these received signals occurs. On the other hand, at multiples of a full wavelength path difference, like 8, 16 millimeters, and so on, constructive interference takes place. The differences are rather common in many practical situations. Since the amplitude of the sound waves differ, interference is only partial to an extent that depends on the angles with respect to the acoustic axis of the transducer and on the reflectivity of the surface. Serious TOF error occur at a small distance and in the vicinity of many reflecting objects. And now it's time to analyze inspection. Compared to 3D vision, the technique of acoustic ranging suffers from a much lower spatial resolution. Conversely, an acoustic TOF measurement system can be implemented in a cost-effective way, provides depth information, and is less susceptible to environmental conditions, except for temperature variation. This explains why ultrasound ranging techniques for object recognition have been studied since the first decade of industrial robotics, presenting in a system based on TOF in the Z-directional and spatial scanning using an XY tape and 2D angular scanning. We discuss three particular approaches: acoustic imaging in air as an alternative for imaging by vision, NDT, and inspection by touch using ultrasound-based tactile sensors. A series of examples for process monitoring using ultrasound concludes this lecture. The goal of any imaging system is the acquisition of an electronic picture from which information about an object size and shape can be inferred, preferably including as many details as possible. In an adverse environment in particular, acoustic imaging could be a good alternative for the well-known optical imaging with cameras. Since the spatial resolution of an acoustic distance measurement is relatively low, some methods of scanning is required to obtain detailed shape information. The performance of an ultrasound sonic recognition system is limited by the nature of sound waves, the properties of the transducers, the quality of the scanning system, the number of transducers, and the signal processing. In general, the acquired image data are sparse and not accurate, which complicates recognition. However, in many applications, the resolution requirements are not severe. Scanning can be performed in various ways. Either the objects move relative to fixed transducers, or the transducers are moving relative to a fixed object. In a robotic environment, a robot can perform the scanning, thereby making use of the many degrees of freedom manipulators to perform 3D scanning all around the object. The encoders in the joints provide the orientation of the scanning range finder. A height map is obtained by Cartesian scanning in a plane above the scene. Sideways scanning enables the reconstruction of the circumference of an object from the position and orientation of the flat or curved side. Several processing algorithms have been proposed to reconstruct the object shape from the obtained data or to classify the object, including digital filtering, holographic algorithms, and artificial neural networks. In all these examples, mechanical scanning is used. The recognition of objects from a fixed sensory system has been studied as well. Usually, such systems comprise an array of transducers with relatively large spacing. For an accurate characterization of large objects from 3 to 10 meters, a set of transmitters and receivers is positioned around the object in such a way that together they cover the whole area of interest. An accuracy analysis of such an approach can be found in one publication. One of the difficulties in such a system is to distinguish between multiple objects and between various shapes returning similar echo patterns. These problems are solved using a set of transmitters and receivers at known relatively position and proper signal processing. For the classification of objects with known shapes, the signature method can be applied. In this approach, no attempt is made to reconstruct the object shape from the range data. Instead, the system is taught to echo-size each object class with a characteristic echo pattern. A typical problem to be overcome in this approach is to obtain image data that are position and orientation invariant. On the other hand, different but similarly shaped objects may result in echo patterns that are also similar. Correct classification on the basis of echo patterns then requires special processing techniques as described in some publications. For objects with clearly distinguishable echo patterns, the method is quick requires simple hardware and software, and is cost-effective. Sound waves reflect the boundary of two materials with different echoes dependent impedance. This property allows the measurement of many geometrical patterns, geometrical parameters of an object, just by applying sound waves to the device under the test, and the analysis of the waves reflecting at existing boundaries. One of the applications is the detection and localization of defects like voids and flaws in a solid, even when invisible at the outside. The detection of a small defect requires waves with a correspondingly short wavelength, and therefore a much higher frequency compared to application in air, typically in a megahertz range. To a certain extent, the size and shape of detect can also be reconstructed from the echo pattern. Another application area is the measurement of a layer thickness. The acoustic technique is used in a wide spectrum of materials and products, ranging from steel plates to layers of clay and human toes. To achieve high accuracy, advanced signal processing is required. As an example, the thickness of a multi-layered structure is measured with an accuracy less than 10 micrometers for the individual layers. With the touch sensor thickness and hardness are simultaneously measured by a combination of acoustic and capacitive sensing elements, where acoustic damping is an unwelcome effect in most of the applications discussed so far. This property of sound can be used to identify, monitor, or determine particular properties of material. It is a suitable method in cases where the relation between the unknown parameter and the damping constant is known by an acknowledged model or by calibration. Again, there are numerous examples to illustrate this technique. We give just one example: the measurement of bubbles in liquid. Both the acoustic attenuation and the speed of sound are related to the volume ratio of two phases. By measuring these parameters over a relevant frequency range, various liquid properties can be deduced or evaluated. The next link is an illustration of the versatility of acoustic sensing as an aid in production and process control. The reference given and only examples of the many scientific papers published on the topics over the last decade. Vibration measurements, example, vibrating cantilever, phase detection over 800 kilohertz sound wave. Spin tracking, example, short range scanning with a megahertz piezoelectric transducer with focusing surface. Respiratory airflow, example, CW wave from piezoelectric transducer with slight different frequency. Liquid level, example, in bottles, 220 kilohertz piezoelectric sensor, pulse mode as an acoustic resonance. Go-no-go decision on product quality, example, quality of foundry pieces, signature imaging, and artificial neural network for identification. Defect detection in food and production line, same method according to this figure. Air bubbles volume on liquid, examples, phase PR system, burst mode at 2 MHz bar. Speed of sound measurement, example, acoustic resonance determination by a piezoelectric, usually ceramic tube. Automotive, example, active suspension control, TOF measurement of backside vehicle to ground. It's used 40 kilohertz burst mode. Body movement, example, head movement relative to a computer screen, using 3 transmitters on the head and 3 receivers near the screen. Paper roughness, using the roughness-dependent reflection on ultrasound. The number of applications where the TOF measurement can be used is also unlimited. And you might be referred to the vast amount of literature or internet publications in journals for the further examples and inspiration. Tactile sensors are used easier to extract shape information on the basis of touch or to provide haptic feedback to the operator or manipulator, as for instance in such a tactile sensor consists of a matrix of 4 sensitive elements, usually called texels. The tactile force is transformed into a deformation of some elastic material, and this deformation is measured using some displacement measuring machine. So, a tactile sensor provides a pressure or deformation image of the object, with which it is brought into contact. General design aspects of tactile sensors have been considered in our previous lecture on a resistive sensor, where the aspect of tactile selection was also discussed. In this section, we focus on ultrasonic measurement of the deformation, which is mostly based on the TOF method. Evidently, it requires an acoustic transmitter-receiver combination for each texel and a means for selecting the individual texel. Usually, a piezoelectric material is used, allowing small dimensions of the texel. PVDF has several advantages over ceramic material. It is available in sheet, it is a flexible material, matching well with the shape of a robot grippers and fingers, and it has a favorable acoustic impedance. One of the first sound-based tactile matrix sensors you may see on this figure shows the basic structure. The elastic top layers of this 3x4 matrix is responsible for the force deforming transfer. Clearly, the echo time changes proportionally to the compression of the layer, and hence the applied force. The spatial resolution is about 1 millimeter. The TOF, determined by the layer thickness and the acoustic velocity, amounts about 5 microseconds. A similar construction, but with the elastic layer in between transmitter and receiver. A completely different approach is described in Engineering Sensor Journal. The basic assumption here is that touch is accompanied by ultrasound. A quartz PVDF sensor at the bottom of the sphere-shaped touch element enables the detection of this sound, as well as the direction and hence the point of touch. The authors expect the sensor also be sensitive to sleep. If, when an object is sleeping, this will generate vibrations and hence sound. This information, as a binary sensor, can be used to control delicate grip. Another type of tactile sensor is able to detect the friction coefficient, basically by measuring the resonance frequencies of an elastic cavity comprising a transmitter-receiving combination. The electrostatic and the electro and piezoelectric devices can act as a transmitter as well as a receiver for acoustic signals. Proper interfacing is required to realize these functions. The electronic circuit discussed in the future and can be used for this purpose. For embedded systems, special modules have been designed to facilitate the interface. The piezoelectric modules depicted in this figure contain the required amplification and filtering electronics for transmitting and receiving pulse. The resonance frequency of these piezo transducers is 40 kHz. Usually, The modules also contain a small microcontroller, which is programmed to send out a pulse over a predefined number of pulses, as well as controlling the moment the sensor switches from transmission to reception. In some cases, the microcontroller on the sensor module also processes the signal. This allows direct interfacing to a host microcontroller system by generating an analog voltage or a communication bus signal, such as logic level asynchronous serial communication. Most relatively simple modules contain a digital input or trigger and output or signal. The host microcontroller system provides a pulse on the trigger input and measures the time it takes for the echoed pulse to arrive at the output, and thus effectively measuring the signal's TOFT. The measured distance amount, L, is a half V times T with the speed of sound. Sometimes the input and output pin on the module are combined to one pin. In that case, the host controller starts by sending a pulse from a pin configured as output to the module, changes the pin to input, and listens for the response. It is advisable to specify a timeout or window when listening for responses specified by the maximum range of the used sensor. Many libraries for interfacing ultrasonic range finders to microcontroller system exist. Typical resolution of this sensor is in the order of millimeters. This section, our conclusion, on applications clearly demonstrates that the applicability of acoustic ultrasound sensor is almost unlimited. The major advantages of acoustic sensing over optical sensing are the lower sensitivity to dirt, smoke, and environmental light. The instantaneously obtained depth information in ranging and the ability to sense inside the object in NDT. Significant disadvantages are the low resolution and the temperature sensitivity due to the temperature dependence of sound speed. The latter drawback can easily be eliminated by an additional temperature compensation. For very high accuracy, one should also consider the effect of humidity on the speed of sound and possible air turbulence introducing noise. When designing a mechatronic system, it is worthwhile to make an extensive comparison between the two basic sensing concepts, acoustic versus optical. Next lecture, we will be studying sensor systems and engineering. And now, I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.